In this video, we're going to be studying continuity of functions. So we're going to start with the definition of continuity. We say that a function f is continuous in a point x0 if we have two things. F is defined in the point x0, and the limit when x tends to x0 of f of x is f in x0. The best way to understand this definition is with a plot. So if I have a function that does something like this, for example, and in this point we're going to say that this one is x0, it has a jump, this continuity like this. Then what's happening here is that when we look at the values at the right of x0, that is, when we go in this direction, the function has this limit, L1. What this is telling us is that the limit when x tends to x0 from the right of f of x is this limit, L1. And when we look at the values at the left, that is in this direction, it has this limit. Let's call it L2. So then the limit when x tends to x0 from the left of f is L2. And what we have is that f in x0 was defined here, so f of x0 is actually L2. But what we have seen in the videos about lateral limits is that when the lateral limits are different, then the limit doesn't exist. So in this case, this function is not continuous. Some books define continuity a bit differently, and it's more of an intuitive way to define it, because they say that a function f is continuous if I can draw the plot of f without lifting my pencil. That is, if I draw the function f like this, and I'm not lifting my pencil, then this function is continuous. If I, on the other hand, start drawing f, lift my pencil and then start again, then this other function is not continuous. And that is true in most cases. But we will see later in another video some examples where there are functions that we can't even draw but are continuous. So this definition is good, but it's more of an intuitive one. The real definition for continuity is this one. So the definition of continuity is based in the definition of a limit. So let's rewrite this definition using the meaning of this limit. And if we see previous videos, we know what the limit is. The limit when x tends to x0 of f of x equal to f of x0. Let's write this in the definition of a limit, that is, in the way we're gonna use to prove continuity in the problems. So for this, what we'll have to do is prove that for every epsilon that's greater to 0, there exists a delta greater to 0, such that if x minus x0, that is this part right here, if x minus x0 is smaller to delta, then my function minus the limit, that is f of x minus f of x0, is smaller to epsilon. So with this written is when we can see the other definition, the more intuitive one, about not lifting the pencil, because when we draw a function and we look at x0 here, and let's say that f is defined to be this number, this is f in x0, then what this is telling us is that when we look at the numbers that are close to x0, that is, numbers here, then what must happen is that our function for those numbers has to be close to our function in x0. That is, the function has to be around this. So our function has no other option but to be something like this. So yeah, near x0 we are not lifting our pencil, and that is why some books use this other definition. Let's continue with an example. Let's say we're given the function f of x that will be defined by parts. It's going to be x squared if x is different to 2, and 5 if x is equal to 2. Let's first draw the function. We learned in previous videos how to draw x squared, so let's just draw some sketch. It's gonna start like this, then in x equal to 2, it's gonna be something different, and it will continue like this. This is just a sketch of the function, doesn't have to be super precise. And for the negatives, it's gonna look something like this. But now our function in x equal to 2, it's defined as 5. So if this would be 4, here we have 5. And this is the value we have here. First, let's look at the lateral limits. That is, let's look at the function from the right. It's coming like this, and it is trying near 2 to be 4. And the same happens from the left. We go in this direction, and the function is trying to be 4 again. So then we know what the limit is. The limit, when x tends to 2, of our function f, let's think of what definition to use of f. Now, this limit, when x tends to 2, it's taking values of x that are different to 2. Because it's a limit, it's not evaluating the function. And when x is different to 2, we have this definition for f. So this is the limit when x tends to 2 of x squared. And this limit, again, we saw how to solve this kind of limits in previous videos, is 4. But 4 is actually different to f in 2 because we have here that if x is equal to 2, f is 5. And that is, this point right here is f in 2 equal to 5. So again, this is another example where the limit does exist, the limit of our function exists, is equal to 4, but the function in x0, which would be 2, has another value, and that value is 5. So then again, f, defined like this, is not continuous. And now some notation we're going to be using and that most books use. We say that f is continuous when it is continuous for every point x in the domain of the function. We just define the continuity for point x0, and now if f is continuous for every point x0 that is part of the domain of f, then we'll simply say f is continuous. And of course there's no video in this channel without a proposition, so let's start with the first proposition in this video. The proposition is divided in 3 parts. We have part A says that we have a function f that is continuous in a point x0. I'm gonna draw simultaneous the drawings. So part A, we have a function that's continuous in x0, that is, it's doing something like this. And we have that f in x0, let's see, this one will say f in x0 is between 2 numbers, a and b. So we have a, that's here, it's smaller, and b, it's bigger, to f in x0. So what this proposition says, that there exists a delta greater to 0, such that when we look at those x that are near x0, then the function is those values is also between a and b. So what this is telling us is that there is some space here. In this case, we have these 2 limits, so this number here would be the delta. And so when we look at all the x here, f of x is this thing, and it's also between a and b. In this drawing is very easy to see it, but in some more complicated function, this is saying that it's always valid. Now the second one says we have two functions f and g that are continuous in the point x0, and so we have that the sum and the product are continuous in the same point, and that if g in x0 is different to 0, then the division of f with g is continuous in x0. This is just remembering the definition of limits, that the limit of the sum is the sum of the limits, the limit of the product is the product of the limits, and that if we had g in the point where we're calculating the limit is different to 0, then the limit of the division is the division of the limits. So just remembering those definitions and propositions we saw in previous videos and applying it to the new definition that it's also a limit. And the last one says we have a function g continuous in x0 and f continuous in g of x0. Then the composition f composed with g is continuous in x0. For those that don't remember, what is the composition? We have f composed with g in some value x. This is a new function that is f evaluated in g of x. So that is why we need the continuity for f in g of x0, because it's the point where we are evaluating it. And the definition for continuity would be exactly the same. The limit when x tends to x0 of f composed to g in x. This is continuous if it's equal to f in g of x0. So the proof for this proposition will not be done in this video because it's very simple. It's just, as I said before, remembering the properties of the limits we saw in previous videos. So if you don't remember about those properties, make sure you do by watching the previous videos and then come back to this one and try and prove all these things. So with this proposition, we can say a lot of things. We can say that some functions are continuous. By this we mean that is continuous for every point in the domain, and we're going to make a small list of all the functions we know. So all polynomials are continuous. All the exponential functions, that is functions f of x equal to a to the power x with a that's greater to 0. All these functions are continuous. All the logarithmic functions and all the rational functions. That is a function of the form p of x divided by q of x, with p and q two polynomials, and this will be continuous in x0 such that q of x0 is different to 0. Because if it was 0, then we have seen again in previous videos that we had a vertical asymptote in x0, and in that case the function would not be continuous. So let's continue and finish the video with a last example. We have the function f of x defined again in parts as x squared minus 4 divided by x minus 2 if x is greater to 2, 3 if x is equal to 2, and x to the power 3 minus 4 if x is smaller to 2. So again, let's start by drawing a sketch of our function. So f in 2 is equal to 3. So let's start by drawing that one. That's this point right here. Now the function x squared minus 4 divided by x minus 2 is a rational function. We know how to plot rational functions, so I'm just gonna draw sort of what the function looks like. It would be something like this. Here in 4, and it goes like a straight line towards infinity. And function x to the power 3 minus 4 is a polynomial, so it looks something like this. And there are a few things we know about this function when we look at the definition. This one. Here we have x squared minus 4 divided by x minus 2. We know this is a rational function, so we said here that this function was continuous when the denominator was different to 0. The denominator here is 0 when x equals to 2, and we have this function when x is greater to 2, so this pink line is always continuous. Here at the bottom we have x to the power 3 minus 4. That is a polynomial, and it will be continuous for every x. So this green line will always be continuous. So clearly the point we have to study is this one, is when x is equal to 2, something is going on with our function, that is here. And there is something going on, because here we have that the function looks like it wants to take this value here, but it's taking this one instead. This value would be 4, and the real value is 3. So we have to start by calculating the natural limits. Let's start with the limit when x tends to 2 from the right of f of x. That is, the limit when x tends to 2 from the right means x is greater to 2, so it's in this direction. It's looking at the pink function here. The function is x squared minus 4 divided by x minus 2. We can factorize the denominator as x plus 2 times x minus 2. And here we can just cancel these two terms out because x is different to 2 because we're taking the limit. So x minus 2 is never 0. And then the limit when x tends to 2 of x plus 2 from the right. X plus 2 is a polynomial, so calculating the limit as polynomials are continuous is just evaluating. So the limit would be 2 plus 2, 4. Now let's calculate the limit when x tends to 2 from the left of our function. Here in this case it would be the green line because we're going in this direction, and the green line is x to the power 3 minus 4. This is a polynomial, so it's continuous for every x, in particular for x equal to 2. And so its limit is 2 to the power 3 minus 4. That is 8 minus 4, which is equal to 4. The two lateral limits are 4. They are the same. So then we just said that the limit when x tends to 2 from the right of f is equal to the limit when x tends to 2 from the left of f. And that limit is equal to 4. And so this implies that the limit when x tends to 2 of f is 4. But the definition for a function here says that f in 2 is equal to 3. And 4 and 3 are different numbers. So f of x, defined as we did above, is not continuous.